Good afternoon. I want to now start with chapter 17. Now, with chapter 17, I will include here phases and phase changes. Remember, we we did talk about when we raise the temperature, but now, and we did not include any I will say changes in phase, and this is why we are going to now start talking about phase changes. Also, in addition to understand like phases and how we there are these are phase changes, we need to study something very important, which is the structure of the materials and how they are really interacting. And one of the most important things that we are going to study in this chapter is the ideal gases and the laws that they are governing that ideal gases. Also, since like temperature, it is related to the translational kinetic energy of the molecules. We are going to study something called kinetic theory, and we are going to derive a definition for temperature, which is like more scientific. We will study also solids and elastic deformation. When a force is applied on a solid, how the solid is going to respond. We are going to talk about equilibrium when we have like phases equilibrium, and also evaporation, and what does that mean in terms of molecules. We're going to talk about latent heats and also phase changes and energy conservation. Then these are all the topics that we are going to study. Now, gases are really the easiest state of matter to describe. They are really, I will say the description is going to be maybe independent of which gas is. Then if I'm talking about, let's say, helium, it's the same as talking about nitrogen, is the same talking about oxygen, is the same talking about any other gas. And therefore, this is going to simplify, because I can just study one behavior and apply this to all the others. Now, we are going to also make some of the assumptions, and these assumptions, they're going to make my study easier, which means I am to have a model. That model, we call it the ideal gas. Now, the ideal gas, it is, I will say, not something that is going to exist, but it is approximately the gas that is thin enough and far away enough from condensing, and the interactions between molecules can be ignored. Okay, then we can ignore the interactions between I will say the molecules themselves, and also between the gas and the I will say the containers walls. Now, we will study first what is called macroscopic. Macroscopic means the big, or like the things from outside. And we are going to include in our study volume, which is V, and that volume, we are going to have it in cubic meters if we are going to have the ideal, the SI unit. Now, the pressure P is going to be in pascals, and that is really the SI unit, or in newtons per meter square. We are going also to include temperature, and temperature, it is in kelvins, which is the SI unit. Now, the first here thing that we might pay attention to is when we are going to study fixed volume gas and fixed number of molecules N. N is going to be the total number of molecules. Now, if we have that situation and we were able to change the temperature, we will find that there is a direct proportionality between pressure and temperature. And temperature here should be in kelvins. Then if the volume of an ideal gas is held constant, and that quantity of gas is fixed because it is enclosed inside this container, then P is directly proportional with T. Now, the second case here is we are really to maybe talk about more about is the volume itself is going to be fixed, and the temperature, it should be T, as I said, in Kelvin. We are talking about something like inflating a tire or basketball. Okay, then more gas is added here, I will say, and we will find that if I will have a fixed volume and fixed temperature T.
I couldn't hear what you said.
All right, I'm sorry, like, okay. Then here, if the volume is constant and the temperature is constant, then there is a direct proportionality between pressure and number of molecules. The third one here, it is another special case where the temperature is constant and the volume here is studied versus the pressure. And here, of course, we should have temperature is constant and the amount of gas is constant as well. There is an inverse relationship between pressure and volume. This is called like Boyle's law. By the way, these are really special cases, but we will talk about the general one now. When we combine all these together, we will say P times V equals K and T. Like, I like this version, this like form rather than this one here. And here the pressure is measured in pascals, V is measured in cubic meters, K, it is a constant called Boltzmann constant, and that is 1.38 10 to minus 23 joules per Kelvin. And N, it's the total number of molecules, and T is the total, the temperature in kelvins. Now, instead of counting molecules, it's gonna be usually large numbers, and it's not maybe preferable usually to count molecules. We can count moles, and a mole is the amount of a substance that contains as many elementary entities as there are atoms in 12 grams of carbon 12, which is actually the Avogadro's number. Then like 1 mole is going to be Avogadro's number of, molecules or like atoms of any gas. All right, it's like a dozen. Okay. Experimentally, the number is Avogadro's number, which is 6.022 10 to 23 molecules in 1 mole. And we can calculate the number of moles of gas by having N capital, which means it is the total number of molecules divided by Avogadro's number. This is going to give me N, which is the number of moles. Now, also, Avogadro's number and the Boltzmann constant, they can be combined together to have something called universal gas constant, R, which is, I think you are more familiar than, Boltzmann constant, and that is 8.31 joules per mole Kelvin. This is, of course, an SI system. As I said, we will have here the pressure in pascals, and the volume should be in cubic meters. And T, of course, always is going to be in kelvins. Now, what I will say here also is Now my equation of state for an ideal gas is going to be modified to be PV equals nRT. And you know that we call it equation of state or the ideal gas equation. And most of you did study this in chemistry. Now, 1 mole is defined as the number of grams of a substance that is numerically equal to the molecular mass of the substance. And here just I'm showing you how you will be able to get or to calculate the molecular mass. Let's assume here I'm talking about carbon dioxide. Carbon dioxide has one atom of carbon and 2 atoms of oxygen. Now for the C, it is 12 grams, and for the oxygen, each is 16. Then 12 grams plus 32 is going to be 44 grams. Okay. For hydrogen, you should know which, I will say here for gases, you should know which gases are really diatomic and which gases are monoatomic. For example, neon here is monoatomic because it's an inert gas. Number of moles in a certain mass is mass in grams divided by molecular mass. Okay. And then this is here the periodic table where you will be provided with, I will say the mass numbers that are needed sometimes for some of the calculations. Now, the atomic or molecular mass of a substance is the mass in grams of 1 mole of that substance. For example, here helium, it is 4.00260 grams per mole. Copper, it is 63.546. Also, we can calculate the mass of an individual atom by giving the atomic mass divided by the Avogadro's number. This one here, it's not the total mass. I'm sorry. This one here, this is wrong. This is not total mass. This is the atomic mass, this number here. Okay, and this is when we want to calculate what is really the mass of each atom. This one here, it is wrong. Okay. Now, for the ideal gas here, we will show you here some of the graphs like pressure versus volume, like Boyle's law. And when the temperature is constant, then PV is P times V is a constant. And when we graph P versus V, this is going to be the type of the graph that we're going to get. These we call them isotherms. For every temperature, we're going to get a different graph. This is for 300, this is for 200, this is for 100. And we can, if we are studying the gas between two states, we can say PIV VI equals P final equals V final. Now, the other law, Charles' law, is consistent with the ideal gas law, which is talking about the direct relationship between volume and temperature. And remember, temperature is in Kelvin again. Now, of course, when we study the volume and the temperature, we keep the pressure constant. And this is really the thing that we are studying here. Now, in this photograph, the balloon was inflated at room temperature, and then we did cool it with liquid nitrogen. Then the decrease in the volume make, it's looking here, it's very clear. This is one of the problems where we have a storage tank that contains 21.6 kilograms of nitrogen at an absolute pressure of 3.65. What will the pressure be if N2 is replaced by an equal mass of carbon dioxide? We have the formula PV, P times V equals nRT. N, it is the mass in grams divided by the molecular mass, times R, the universal constant, times T in kelvins. Now we can create that equation for nitrogen, and we can create the same equation for carbon dioxide. And then we divide to get rid of the things that they are the same or equal. Then I will say mass is going to cancel, and also we're going to get rid of RT, and then finally P carbon dioxide divided by pressure of nitrogen will be the molecular mass of N2 divided by the molecular mass of CO2, and that is 2.23 atmospheres, calculating the pressure of carbon dioxide. This is another problem here. An automobile tire is filled with a gauge pressure of 200 kilopascals at 10 degrees Celsius. After a drive of 100 kilometers, the temperature within the tire rises to 40. What is the pressure within the tire now? Then, like here, we have the same enclosed amount of gas. The number of moles is constant, and the volume also here is constant, but we can now create an equation for the first state and the second one, and we will say P1V1 equals nRT1 and P2 times V equals nRT2, and then we divide to get rid of the constants, and then finally we will be able to calculate the pressure, the second pressure, to be 33 kilopascals. And you can see here that at the temperature of 10 it was 200, and at 40 it is 333, which is reflecting the relationship between pressure and temperature, absolute temperature. Now, this is the new topic here, the kinetic theory of gases, and it is now relating microscopic quantities like position and velocities, you're going to see, to macroscopic ones that we were talking about, like pressure, temperature, and volume, but usually pressure and temperature. Assumptions. N are really the number of molecules. They are identical. They have, all of them, they have mass M, and they are inside a volume V. Each acts as a point particle. Okay. The second assumption, they are moving completely random and always obey Ohm's laws. The collisions are really elastic. All the collisions, they're collisions with other molecules and also the collisions with the container's wall. Now here we can say also that the pressure is the result of collisions between the gas molecules and the walls of the container. And it depends on the mass and the speed of the molecules and on the container size. Here, we will say pressure equals F over A, and that F can be, like here, we can calculate the, actually the momentum here. It's when it is coming, hitting the wall, is going to be PIX equal negative MVX, and when it is recoiling, is going to be MVX, and the round trip is going to be 2L. Then we will be able to get that this is really the expression MVX squared divided by the volume. Now, not all the molecules in a gas will have the same speed. Okay, they have different range of speeds, but there are like there is a speed that is gonna be like maybe a maximum speed, and you're gonna have most of the molecules, they're gonna have that speed. Now, that their speeds are represented by the Maxwell distribution, which is the normal curve that we can see, and depend on temperature and also on mass of the molecules. Now we replace the speed in the previous expression for pressure with the average speed, and we will say P is is gonna be like we can include all the other directions, the other two dimensions, and from that we can also make this equal to the equation of like a state, which is the PV equals nRT. Then therefore we are going to find out that the gas pressure is proportional to the average kinetic energy of its molecules. It has to do with that. This is really again another thing that I was able to derive for you, that just to show you here that the pressure is 1/3 Nm, like this equation here, can you see it, equals nRT. And then I canceled the ones that I have here. I replaced K with I replaced R with K over NA, and then I canceled NA, and finally I was able to say that the kinetic energy is going to be 3/2 kT, and K, remember, it is Boltzmann constant. Now the kinetic energy here, it is the average translational kinetic energy per molecule, and it is related to temperature. This is why we will define temperature as related or a measure to the average kinetic energy of molecules. The translational, sorry, again, the temperature, it is the average translation, it is related to the average translational kinetic energy per molecule. And this is what I was talking about. Comparing this expression with the ideal gas law allows us to relate the average kinetic energy and temperature. And this is the expression. Now the square root of V squared average is called the root mean square, RMS speed. And solving for the RMS speed, like the VRMS, we're going to take the square root, and then it's going to be the square root of 3kT divided by m. And here, remember, m, it is the mass of the gas, the mass. SI unit, of course, it is meters per second. Now we need to know that the RMS speed is slightly greater than the most probable speed and the average speed. The average speed, it is the one that is in the middle, and the most probable is where the peak of the Maxwell distribution, and the VRMS is slightly, I will say, greater than the most probable speed and the average speed. Okay. Now, the internal energy of an ideal gas can be calculated as the sum of all the kinetic energies of molecules, and we will find that is going to be U equals 3/2 N times KT. Then this is the internal energy of a monoatomic ideal gas. Monoatomic means it has only one atom. Then what this applies to helium, neon, I forgot what, helium, neon, argon, and all the members of the last, I will say, column of the periodic table. What is the average translational kinetic energy of a molecule in an ideal gas at 37? It has to do only with temperature, and that temperature should be in kelvins. Then first you have to calculate T as 37 plus 273, and then you will be able to calculate the kinetic energy, the average translational kinetic energy of these molecules. Now, what is the RMS speed of air molecules? And mainly we are talking about nitrogen and oxygen at room temperature. Room temperature is 20 considered, like some of the people, they're gonna consider 22, but usually we need maybe to say if it is 20 or 22. And VRMS is the square root of 3kT over M. And I will find first what is the mass of oxygen and what is the mass of nitrogen in kilograms, and then I will substitute this into the equation, and from that I got VRMS equal 480 meters per second for oxygen, and VRMS equals 510 meters per second, and they are well below the average, the escape speed of the Earth, and this is the reason why they are going to stay in the atmosphere. Now, solids and elastic deformations. This is talking about when I have solids that they are going to be exposed to forces. For example, here I have this tube or whatever, and I have applied force that is stretching, pulling on opposite ends of a rod can cause it to stretch. Now, there is a general relation that we are going maybe to talk about it like more than one more time. Stress equals a constant times strain. Now, the strain, it is measuring the deformation, and the stress, it is measuring the force per unit area. And the number here, the constant, it depends if I'm talking about like tension or changes in I'm talking about tension and or compression, or if I'm talking about shear forces, or if I'm talking about bulk forces. Now, when we talk about stretching or compressing, we are talking about what is called Young's modulus. That constant that I was talking to you about here, we are going to call it Young's modulus, and the amount of stretching will depend on the force. Force per unit area equals Young's modulus times the stress, and the stress here, the strain, sorry, and the strain here, it is the change of the length divided by the original length, and I will say this is doesn't have a unit, but F over A, it has pascals, then Y, which is the Young's modulus, is going to have units of Pascal. Another type of deformation, it is called shear deformation, where opposite sides of the objects are pulled literally in opposite directions. Then these forces here, look at the force F, and this is the force. I'm assuming this is a textbook that we are going to expose it to these two forces. Then there is a deformation, and that deformation, it is that delta X divided by L0. Now, as expected, the deformation, again, it is proportional to this force, and the stress here equals the shear modulus times delta X over L0. Also here you will find there are some of the tables, like maybe I did not mention this. This is Young's modulus for various materials, and I will say also we have here the shear moduli for different materials. Here is one application of the formulas. We have 15 centimeters long tendon was found to stretch 3.7 millimeter by a force of 13.4 newtons. The tendon was approximately round with an average diameter of 8.5 millimeter. Calculate the Young's modulus of this tendon. The first thing I want to bring to your attention is that the cross-sectional here area, it is a circle, and this is the reason why we are going to calculate it as pi times r squared. R is the radius, and usually you might be given the diameter. Then you will be able to find the radius by having the diameter divided by 2. Also, I want you to pay attention to your units, non-mixed units. Then if I have centimeters, you need to convert this into meters. And we did that here, 0.15 instead of 15. And this is the area, pi r squared. This is the force. And this one here, it is that change in the length. Also, it was given in millimeters, then we did change it into meters. Y will be 9.6 10 to 6 in newtons per meters square. Now, I will say, now finally, if I have a solid that is uniformly compressed, it will shrink. Then there is an initial volume and there is a final. And because the relation between the pressure and volume is inverse, and this is the reason why we're going to get here a negative. Now also we're going to have changes in pressure will equal negative B. B here, it is the bulk modulus, and times delta V over V0. V0 is the initial volume. Now we have here given to you like bulk moduli for different materials. At depth, which is 2,000 meters in the sea, the pressure is about 200 times atmospheric pressure. By what percentage does the interior space of an iron bath sphere's volume change at this depth? Then we will be able to say delta P equals minus B delta V over V0. And then I can actually rearrange my terms. And then we are going to start by 1 atmosphere, and the change is going to be 199 because it's going to be 200 minus 1. Then it's going to be 199. And we will be able to find what is really the change, the fractional change in volume, and also we can express it as a percentage. Now, of course, if we will be able to apply forces on the object continue, we will find that there is a region that we will have, I call it elastic region, where Hooke's law will be applied stress proportional to strain. But after that, we are going to have a deviation from the Hooke's law, and after that, we will terminate that elastic region, and we will create kind of permanent deformations in materials, and we don't want to use materials in this region, because this means that we are ruining them. Okay, now the last topic here, it's not the last, but like mostly we are going to talk about phase equilibrium and evaporation, and then we are going to talk about how we're going to apply energy conservation and find out about phase changes. Now, if we have a liquid that is in a sealed container, and there is vacuum above it, some of the molecules in the liquid will evaporate, and once a sufficient amount of these, some will begin to condense back. Equilibrium is reached when the numbers are really constant, remains constant. Now, there is something related to the pressure of the gas, and also the vapor pressure and the temperature. You can see here that we call the pressure of gas when it is in equilibrium with the liquid, like it is just kind of have the two states in equilibrium. We call it equilibrium vapor pressure. And this will depend on temperature. For example, here in the diagram, I have it like 80, and that is at the mountain top. 100 at the atmospheric pressure. 120 at the pressure cooker. Then like it will depend on temperature. Now that curve determines the boiling point of a liquid. When the liquid is boiling at a temperature at which its vapor pressure equals the external pressure. Okay, now this explains why water boils at a lower temperature when we have lower pressure. This is really the curve that we usually talk about, like all the three, I will say, phases. And I will say we have mainly the three states: gas, liquid, and solid. Now you can see that there is something called a fusion curve, which is when the solid is going to be converted into liquid. There is a sublimation curve here, and that is when the solid it is converted into gas. And there is also between liquid and gas we have the vapor pressure curve. All of these are really intersecting at a point called triple point. Now there is a point, we call it a critical point, and when you know that when the gas, when the liquid reaches that critical point, there is no longer distinction between liquid and gas. Then there is like kind of fluid phase. It's not this or this. Now the fusion curve is the boundary between solid and liquid. And along that curve, they exist in equilibrium with each other. Then I will have solid and liquid. Almost all materials have a fusion curve that resembles A. Okay, this is the one for all the materials. Now the second one in B, it is for the water, which is having unusual properties near the freezing point. And this is why it's looking different. Finally, sublimation curve marks the boundary between solid and gas, and the triple point is where all the three phases are in equilibrium. And this is what is called the phase diagram. Okay, now we were talking about when a liquid in a closed container will come to equilibrium with its vapor. However, an open liquid will not, as its vapor keeps escaping, because the molecules, they will escape. It will continue to evaporate or vaporize without reaching equilibrium, as the molecules that escape from the liquid are the high energy ones. This has the effect of cooling. Then we will say evaporation, it creates cooling. If we look here at the Maxwell distribution for the speed distribution for water at different temperature, we see that there is not much difference between the 30 and the 100 curve. That means that if 100 degrees Celsius water molecules can escape many 30, well, also then evaporation can occur at all temperatures. Now, also here, this same evaporation process can cause the planet to lose its atmosphere because of this, as I said maybe before when I was calculating for oxygen and nitrogen, I told you that they have these kind of speeds that they are really low or well below the escape velocity of the Earth, which is 12,200 meters per second. This is the reason why they're gonna stay in the atmosphere. Now, here I will talk now about adding or removing heat when I have phase changes. And this is really the heating curve of a substance. It can be any substance, but this one, it is just for water. Okay? Now, if I have ice at -20, and let's assume I have a thought experiment that I'm going to start warming up that negative 20 degrees Celsius ice, then I will say the ice will not melt until it reaches zero. And then when it will reach zero, it will here be constant at zero until all the amount of ice is changing into liquid. And here we are going to have liquid and gas are really in equilibrium. Now, did I say liquid and solid? They are going to be in equilibrium. Then now here, all the water, all the ice now is changing into liquid. Then I can raise the temperature from 0, 10, 20 till I reach 10. And here I will say, I'm gonna get a new plateau or like a new constant where I will have the point where I call it the boiling point of water, which is the 100 at sea level, of course. And then after that, the steam can be any temperature above 100. Now, the latent heat, it is the heat required to convert from one phase to another. And we have latent heat of fusion. We can have latent heat of evaporation. The latent heat can be added or removed from 1 kilogram of substance to convert it from one phase to another. During that conversion process, the temperature is going to stay the same. Q equals M times L. M should be in kilograms, and L, it is the latent heat in joules per kilogram. Here are some of the latent heats. You will see these in your quizzes and your exam. I listed these for use because you might need these for any calculation. Try using it. Okay, here, how much energy does a freezer have to remove from 1.5 kilogram of water at 20 to make it at -12 degrees Celsius? Now, you need to break this into steps. This is very similar to the quiz that I'm giving you. And like I will say, not the quiz, I will say what is called the exit ticket for this chapter. Okay, first I need to cool down the water to 0. And this is the red. MC, MCAT for W for water. And remember, temperature, it is always final minus addition. The second one, change the phase into solid, and this is MLF, which is the mass times the latent heat of fusion. Now the third term, it is cool the ice to -12. Then now I have ice that opposite to what I did in the curve. Okay, then it's going to be MCAT again, but for ice. Remember here, this is C for water. It is 4186. It is different from C for ice, which is 2100. And then I will add all the 3 Qs, and this is going to be 6.6 10 to 5 joules. Now, this one here, it is at a reception of 0.5 kilogram chunk of ice at -10 is placed in 3 kilograms of iced tea at 20 degrees Celsius. At what temperature and in what phase will the final mixture be? Okay, consider tea to be just water. Ignore heat flow to the container. First, determine final phase. Consider the energy release at each step. Cool the tea to 0, warm the ice to 0, and change the phase to solid, which is the ice. Then I will calculate these quantities. Now, to turn the ice to water would take 177.5 kilojoules, sorry. And this is not enough to bring the T down to 0. final phase will be completely liquid and is going to be at a temperature between 0 and 20. And that is, I will say, heat gain is going to be heat loss. And this is what I will do to find what is the final temperature. This is the summary of the chapter. And that's it. Thank you. And see you in chapter 18.